Good afternoon, everybody. It's really a pleasure to be in this city, San Francisco, southern San Francisco, and present my results on my research in the OMICS Industrial Engineering Conference. Topic of my presentation is distributed cloud-based manufacturing integration through intelligent information sharing. Give you a brief introduction. I have about 40 slides, so I'll check time. Maybe I may skip some of them, but if anybody is interested in proceedings, there is my email, so if you send me email, I can send you a complete set of slides. So, introduction, background, process planning model representation, distributed planning applications, agent-based methodology, and conclusions. First of all, I want to acknowledge that this is not work on only myself. This is work of 10 years work with me and about a dozen students doing their master and doctoral research. That's their work, so I'm just here presenting it. Intelligent integration is information sharing is seen as a necessary ingredient for global competitiveness, as Ping Ji already mentioned. So we have to deal with information in many different fields. Integrative information involves transfer of data between applications, data and modeling integration, distributed processing, and incorporation of knowledge into planning into all our tasks. Product data should be transparent between different software applications. I didn't mention there, but ERP is definitely one of them. Data need to be saved, transferred, and recreated whenever necessary for distributed processing. And this approach enables global distributed enterprise, knowledge economy, and excellence, cloud-based manufacturing, and product configuration remotely and mass customization. I'm going to skip my premises here just to save some time. I'm going to, what is manufacturing, what is integration? Manufacturing is, I see it as any activity that creates new value, usually seen as creating new product using metals, but in reality, manufacturing is making foods, manufacturing is making ships, making airplanes, all these are manufacturing. Manufacturing development can be seen as answering to 5 or few simple questions. Why, what, how, where, and when. And from these simple questions, we basically build a list of activities that have to be accomplished to convert idea, either from customer or from end designers, innovators, to product that can be sold to customers and receive profit. There is a lot of activities there. So it is not simple answering these 5 questions. There is a lot of activities, and this next slide shows a sample of these activities in metal manufacturing, in prismatic parts manufacturing, starting with several activities like design, feature recognition, process planning, resource planning, scheduling, and such. There is a variety of tasks that have to be executed. Important point of this picture that some of tasks are unique for single expertise, like mechanical design or like scheduling, while many of these tasks require shared expertise. And one of them is process planning. You cannot do process planning if you don't know materials. You cannot do process planning if you don't know what is your equipment in your shop floor. So you do have to have shared expertise, and this is where idea of integration, integrative approach comes into mind. So to solve this problem, we propose integrative process plan model that has 3 components: manufacturing planning object model, feature object model, and machining process model. But before that, it is important to understand that this planning is happening in 3 dimensions. These dimensions are time. So we make decisions in time. Today we make decisions about product design. 2 weeks later we make decisions about its planning, and then 2 weeks later we make decisions how to make it, which equipment to use. Second dimension is variety, which is essentially saying that there are 2 facets of variety. One is alternatives. Second is product mix. I'm going to just use terminology. So no company makes one product. there is no product that makes only one alternative. So customers, mass customization requires from us to make products that are easily customizable, that we have built in advance options that we can offer our customers. When they choose particular options, we know what to do. And third dimension is aggregation, which corresponds to hierarchical structure of our modern enterprises and the hierarchical structure of decision making. We can focus on a single mechanical design, a lower level. We can focus on a single machine in our shop floor, make plans how it is to be done, or we can focus on a complete facility in which, for example, we address scheduling problems. And nowadays, we have to focus actually one level up here that I didn't show here, is actually planning for facilities on different locations. And actually, this is what I already explained. So there are a few things that I mentioned. So time dimensions, variety dimensions, aggregation dimensions, and few examples. When we make decisions, we walk between these levels, between these dimensions to appropriate place. So to address in this approach, we built integrative process planning model having these three components, as I mentioned. Manufacturing planning object model is model of information, content, data necessary, and knowledge, of course, I'll mention later, for manufacturing facility or enterprise, modern enterprise as a whole. We didn't focus on everything. But we are integrative, meaning we can actually propose approach that can be integrated with other work. For example, we do not work on scheduling. We don't work on supply chain. It's a big extension. So few objects here allow us here to store necessary information, for example, that is needed for MRP or ERP system. Feature object model is second component of data representation. Basically, it describes product designs in terms of features, which are unit of manufacturing in this approach. It has taxonomy between these different features. And again, this example shows you manufacturing features in metal machining. But my proposition here that this equivalent structure has to be done in different manufacturing domains. And third object is machining process object. Again, with the example of prismatic part machining. Again, this is classification or taxonomy of these objects, of these processes. Purpose of this is that every process is capable of doing something, making some shape. And we have to basically make matching an appropriate level. Again, approach here is that for different domains, this knowledge can be extracted within same framework. Having these tools, there are a few things that are happening when you talk about product configurations. You have to worry about knowledge management and apply knowledge-based reasoning. Important concept here is generation of design options and planning alternatives. As I said already, two reasons for design options, planning alternatives. One is reason is offering options to our customers to buy our product. If they have, we tell them, okay, if you choose this option, we are going to deliver in 2 days. Is better approach than if we say, if you choose this option, we're going to deliver in 2 weeks. So if you didn't think about options and alternatives, answer would be 2 weeks. But if you do this in advance, answer is going to be 2 days. Second one is making decisions. Whenever we make decisions in collaborative environment, we have to approach our task with several alternatives in our pocket and hope that other side has also several alternatives in their pocket and we can match most promising alternative. If I come up into decision-making process, say, this is my approach, only one, and we have to negotiate or collaborate, it's not much space for collaboration. Because I didn't think about what if other side says, okay, it doesn't work for me. I don't have equipment. It's too costly or something. Other tools are distributed applications of this decision space through internet, agent-based modeling, and neutral knowledge and data representation. Let's talk a little bit about knowledge. So in this domain, we identify several types of knowledge. Procedural knowledge, usually represented as rules. Okay, if there is some conditions, I have to perform some action. Declarative knowledge represented as relations, statements about the world in which I live. Experience knowledge, which is very important. We have actually haven't worked much in this, but we learn in our job every day. And when you start your engineering or machinist job or technician job today, and 5 years along the line, you are going to know more about that job and now how it's to be done. And you basically build this through entities relations between different entities. Few illustrations. So this concept knowledge management. This is slide that shows precedence relationship between various manufacturing processes. Something has to be done before something else. And this is knowledge that's available in literature. This is knowledge that if you ask machinists, it's commonly available. When you want to make an automated system, this knowledge has to be somehow incorporated into our systems. And essentially, we use initially we use XML representation shown here. This is a representation of very same knowledge, just how a computer can understand it. But also, we are extending this right now into developing something that's called manufacturing ontology. We want to capture semantic of the data represented in message between these different objects. We are building IMPlanner ontology based on previously built model. Every semantic concept consists of several concepts, and basically there are properties and relations between them. And using ontology, we can define complex data structures. In our IMPlanner ontology, we have a root concept called manufacturing concept. We extend this concept to manufacturing features, manufacturing processes, and manufacturing activities, and basically start extending further and further. And then we ask what are properties of these particular objects and how they are related to build that ontology or knowledge. We applied several methods for knowledge-based reasoning. I mentioned rule-based systems already. We applied case-based reasoning and intelligent search into problem space. Illustration for this, I think I mentioned it already about design options, planning alternatives. Again, enables instant product reconfigurations and order configuration. I'm going to show essentially illustration of these alternatives. This is simple mechanical parts with identified features and required precedence in their processing. Depending on what equipment or resources are available to make this product, you can end up with a network like this, in which any part from start node to end node is a feasible process. And this is a result of built-in knowledge with generation of alternatives. So any part is feasible, and again, you can apply optimization and say, okay, which one is optimal? Point of having this network is that this optimization algorithm may be running differently in different stages. Equipment fails. So if I applied optimization 2 weeks ago and I got one path through this network and I want to use that path today, if machine is failed, I cannot use it. I need to apply different, I actually have to exclude this machine from consideration in order to reapply optimization. Is it time? We have, what, 5 more minutes, right? 3, 4 minutes. So I'm going to skip a few more slides here to speed up. Distributed applications, this is our decision space. What is happening here, this shows that these 8 applications are done on different geographic locations, different time zones, and they have to work in sync within this manufacturing process model within these 3 dimensions. And they see some of them work in 1 dimension, some of them basically jump between different dimensions in terms of aggregation. We have built several applications using this framework. First of all, we built prototype. We call it IMPlanner system that actually supports data modeling for these applications and basically feeds all these applications. Manufacturing feature modeling, rule-based process selection, manufacturing cell formation, and scheduling and simulation of flexible manufacturing systems. I have few here slides that show, illustrate results from this application. I'm going to skip them in sake of time. I'm going to actually focus on what is current work, which is agent-based modeling. So right now we are doing 2 approaches. One is formalizing ontology. So we have built a lot of manufacturing processing, manufacturing planning knowledge. We are right now doing work with several students on formalizing this knowledge into ontology. That our plan is to share it on the web and offer it to research community for comments, additions, and extensions. And the second one is converting this distributed application into multi-agent system. Example of multi-agent systems, you have a service A and service B, and task has to visit both of them, which is what happens in reality. Again, it is very suitable for distributed processing. Illustration of this processing, we built a small prototype for this agent-based system that basically to demonstrate a feasibility of our approach. This is an in-house build model, but then later we extended it, and now we are calling it IMPlanner mass methodology, in which we build open market of services with negotiation capability. A negotiation to say, okay, you ask my help, I can decide if I want to give you help or not. I want to apply to all requests my own criteria. And this is architecture in which we are working right now. Again, multi-leveled, so that basically we can distribute different tasks and different alternatives. Usually when you do an agent-based system, you have agents that are, first of all, collaborating to accomplish tasks, but second, you can have agents that are competing for the same task. So we're going to build these models into this system. And I think I'm going to finish here. Few conclusions. So we propose generic framework for distributed integrative modeling and planning. And then we propose data model for design and manufacturing with benefits of reduction of order delivery times, product development cost, and manufacturing cost. We have implemented prototype, and we ran several distributed separate applications. Current work is transferring these tasks into distributed agent-based processing with formal ontologies. Thank you. And that's my presentation.